Good afternoon, everyone. Welcome to another AMS Weather Band webinar. We're really excited you could spend some of your afternoon with us or whichever time zone you're in. We're really excited to have Jared Rennie here today. Jared is a research meteorologist at the North Carolina Institute for Climate Studies. He joined the NCICS in 2010 and currently supports the maintenance and expansion of major land surface data sets, including working on global historical climatology and the climate reference network. So he does an amazing amount of research with climate data needs on national and international scales. So we're really excited to have him here to talk about his latest research into heat severity and how that impacts us as humans and our weather as well. So thanks so much, Jared, for being here, and I will hand it over to you to get us started.
All right, can you hear me? Good, you good? Awesome.
Yep.
Thank you all for having me. I really do appreciate giving this talk. I do a lot of stuff with AMS, so anytime they ask to help out in some facet, I'm always happy to do that. And this type of research is really interesting for me. For those that know me through personally or through social media, in that I do not like the heat. So I've actually kind of focused that towards some research, and that's going to be what I'm talking about today. For those that are wondering, I am in a federal building, so I have to have a mask on during this talk. So I will do my best to try to project through the mask that you can all hear me. But if there's any technical issues or anything, someone flag me down. And as they had mentioned, I will happy to answer any questions you have at the end. So the title of this talk is "How Hot is Too Hot? Examining heat severity using something called the United States Climate Reference Network," and I'll talk about that a little bit later. Hang on a second. There we go. So for those that do subscribe to the AMS journals, a lot of the stuff I'll be talking today was recently published earlier this year in the AMS Journal of Applied Meteorology and Climatology. So if you want a more technical description of what I talk about today, go ahead and check out this journal article that I worked with Mike Pilecki and Howard Diamond of NOAA's NCEI, as well as Sean Hauser and other folks at the North Carolina State Climate Office. So let's jump right into it. So this is a graphic that the Weather Service provides every year about the number of weather-related fatalities. And if you go by the 30-year average from 1991 to 2020, heat is essentially the number one for amount of fatalities. Using the last 10 years, it's tied with flood and tornadoes, but nonetheless, it's almost like a silent killer per se. You know, people think that, with big weather events like hurricanes and tornadoes and flooding and rip currents, like that, people would think that those have more deaths, but heat can be just as bad. And there's actually another study outside the NWS that they've claimed that because heat can lead to other health effects, that this number can actually be a little higher as well. Speaking of health, heat can affect us in many different ways, but it's really prevalent in the health sector. There's, obviously when you have really warm temperatures in the summer, much warmer than normal, that can affect pretty much lots of things: how much you stay outside, how much you work outside. But there's also sort of these indirect effects that people may not realize. So for example, people that are, if you're elderly, over 65 years of age, or young kids, they're more susceptible to having heat-related illnesses. And there's other things as well, including, how a city is built. If there's, a lot of buildings in your downtown area, a lot of concrete, a lot of asphalt, that can create something called the urban heat island effect. And then, if you are in a downtown area, there may be a cooling center that you can go to. Like, let's say your home doesn't have air conditioning, you may be able to go to a cooling center that the city has set up, which can be advantageous for people that live in the city, but maybe if you're in a rural environment, that's not necessarily the case. And it's not necessarily just the heat as well. There's also humidity, there's wind effects, there's being out in the sun. So if you're a worker, that work outside all day, being in the sun can have, some effects as well in all this. And then this can lead the sort of the health outcome at the bottom of this graphic here can lead to either heat-related illnesses, hospital visits, then obviously mortality. So this is a graphic that the Weather Service develops, and it talks about, two kinds. There's heat exhaustion and heat stroke. And for those that are unaware, there's actually differences between the two. And this is actually a really good graphic that the Weather Service had created. And, these are the symptoms that you experience under either, and then what you can do. And as you can see, in one case, you call emergency services, you call 911, but in the other case, you try to do some things first before you may have to do that. And again, there's other heat-related illnesses that can come in addition to this, like cardiovascular issues, diabetes prevalence. So there's, so long story short, heat can be a huge issue for most of us. But that's not exactly why we're here. This was just more of an introduction. It's like, how do we define heat severity? Like, what is a bad heat day? And, if you're looking for an answer from me, I apologize, you're not going to get it, because the literature right now, there isn't necessarily one definition of a heat wave or a severe heat event. You can define it multiple different ways. And actually, one of my colleagues, Tyler Harrington, made a graphic similar to this, and I thought it was really good at conveying the different types of ways you can do it. And it's almost like this puzzle piece where, you could kind of go along the line here and come up with multiple different thresholds. And so there's basically 4 pieces to this. The first piece is, what metric we're looking at, what temperature metric. Then, what part of that metric are we looking at? Are we looking at the daytime value? Are we looking at a nighttime value, or the combination of both? And then, a threshold, which I'll talk a little bit more about that later, but there's certain ways, a number of days above a certain threshold, and that can be a fixed or an absolute or a relative threshold. And then finally, the number of days, and that could be up in the air depending on who you talk to. There could be a 1-day event, it could be a 7-day event. So to kind of show you like an example of this, I'm originally from New England, just outside of Boston, Massachusetts. So when I would watch the local TV stations, they would actually, in the summertime, they would say, okay, we would look at temperature, and we would look at the maximum temperature for the day. And then, if you had 3 consecutive days that the max temperature was above 90 degrees, that was considered a heat wave. But that works really well for Boston, but that may not necessarily work for Miami, let's say, because Miami, they typically have temperatures, at about 90 or higher for a good part of the year, whereas it's rarer in Boston. So this is just kind of one example of how it would work. So I'm going to spend a good part of this talk talking about 2 of these columns, the metric that's highlighted here in green, and then also the threshold piece. And I'll briefly talk about the other 2, but most of this talk will explain the metric and the threshold. So let's talk about the metric. So there's generally 4 that's, at least in the science community, and in some cases the public are aware of. Obviously, there's the temperature. We call that the dry bulb temperature. It's your typical, you put a thermometer on a weather station. It's the most, every weather station pretty much has one. And it's just what's the air temperature for that particular area. But then there's 3 others that incorporate a little bit more than just temperature. So we have heat index, apparent temperature, and then something called WBGT. That's an acronym for wet bulb globe temperature. And I'm going to take a minute to talk about all 3 of those. So the heat index is kind of the common one. That's the one that the Weather Service really uses. It's been around for a little over 30 years. It has a funky little equation, but essentially takes into account heat and humidity. So it takes in the temperature, the relative humidity, and goes through a regression equation to generate a value. And typically, for most areas of the US, the heat on a really hot day, when it's really hot and really humid, it's almost like what the body thinks it feels like. So, for example, I'll just kind of pick off an example here. Let's say it's 94 degrees in a certain area, and you have a relative humidity of about, 70 or 65%. So takes you to about, it actually feels like it's in the hundreds, 114. And this has been a really successful product. It's been, as I said, it's used by the Weather Service. They use it a lot when they determine heat severity. There's an older version of this equation called apparent temperature. And they have multiple equations. I'm going to just focus on this one here. But this also takes into account heat and humidity. But what it also does, it takes into account wind. So when it's really, if you're outside and let's say it's really warm and your body is, producing sweat, the wind, what it can actually do is it can help evaporate the water off your skin. And through some laws of physics, it actually creates a cooling process. So a windy event, there's some wind out that actually can make you feel cool and refreshed. And that's kind of where apparent temperature comes in. It's not as popular as heat index, but it is used in certain areas. NOAA's National Centers for Environmental Information, that's actually the building I'm in. They archive basically all the world's weather data. They have a data set of apparent temperature. And it's been used in some studies too. There was a study from, I believe, the University of Georgia, and they created a heat vulnerability index using apparent temperature. And that's what you see on the right here. So the darker colors indicate that those counties are more vulnerable to adverse heat events using the apparent temperature. And then there's this other one that it's been around since the 1950s, but has kind of gained a lot of momentum in the weather community over the past, let's say, 10 years. And it's called wet bulb globe temperature. And it's a pretty simple equation, but it takes into account a little bit more than heat and humidity. It includes the wind, and it includes the sun or lack of sun, and then the sun angle. And again, because, we talked about the wind a little bit, but the sun, if the sun is beating down on you, that can have your skin heats up as a result of that. And that can, be negative to your body, especially if you're an outdoor worker. So like, obviously, organizations like OSHA say that, well, if you are outside, you try and get into the shade as much as possible for exactly that reason. So it was initially adopted in the 1950s by the US Air Force, but a lot of groups, including the Weather Service, start using it, and also a lot of athletic organizations. So down here, I'm in Asheville, North Carolina. So I believe football associations or athletic organizations in North Carolina, in Georgia, and in other places, they actually use wet bulb globe temperature as their metric to determine how they're going to, practice for that day. And they have, I believe this was the Georgia Athletic Association, but they had set these standards for what you do when the wet bulb globe temperature is a certain value. And, so if it's, less than 80 degrees Fahrenheit, you have unlimited activity, you could be outside, no issues. But then as you start to get a little higher, there's more precautions, closely monitor people that may or may not be acclimated, do what rest breaks, water breaks, try and go in the shade when you can. And the highest level here, when it's at 90 degrees or above, they actually tell you don't be outside, suspend practice. Now, one of the reasons why I'm showing you this graphic is the numbers. Even though it's on a Fahrenheit scale, these numbers don't seem that dramatic. So like, for example, if you have a heat index value of 115 or 120, that's really high. But if I tell you, hey, it's 90 degrees, you can't be outside, people go, well, that's actually not bad. 90 degrees is fine for some areas, right? Well, because this takes into account solar information and wind information and relative humidity information, is that these values have severity levels that are lower than human perception. So this creates a problem if you're using this metric as a forecast, which the Weather Service does. And actually, this graphic shows it here really well. On on the left, there's a Weather Service office in Raleigh, North Carolina that uses this metric a lot. And then on the right, this is actually sort of one of our model outputs, or one of their model outputs from the National Digital Forecast Database. And, again, what they're saying is values of the upper 80s and low 90s are considered dangerous or, hazardous. But from the public perception, they go, hey, it might not be that bad. So it's going to be a very interesting communication issue if this metric continues to be used down the road. So where do I fit in all this? So during the introduction, it was mentioned that I work on the United States Climate Reference Network. It's about 139 stations across the US. And they're weather stations on the ground, essentially, but they're not like your typical weather stations like you would see at an airport. These are more located in rural areas. They were actually specifically designed to not have any urbanicity, for lack of a better word, happen over like a 50-year period. So the climate of these areas, they're more remote. These are in more rural areas, but they were designed so that the vegetation and the lack of buildings that are there now would continue to be the same, so that it would help it would help sort of monitor the climate over this period. And the other nice thing about this network is that they have all this excellent equipment. So they have your typical thermometer on there. They have a hygrometer for humidity, but they actually have pyranometers, which measure solar radiation. A lot of weather stations don't necessarily have that. So we were able to, and it has anemometers as well for wind and wind speed, and then obviously wind direction. So we're able to take this information, which, by the way, we have hourly data, but we also have information every 5 minutes. And so as a result, we had developed some code that was able to estimate all these variables I talked about before. So we have a heat index product, we have an apparent temperature product, and we have a wet bulb globe temperature product. So we were able to do that at these sites, which it goes back to 2009. So we only have 11 years of data, and I will kind of come back to that in a little bit. So I've already talked about the metrics, the 4 different metrics that can be used. And these aren't the only 4, by the way. There's other ones out there as well, but these are kind of the 4 that we've sort of focused on. I'm going to briefly talk about the type. So again, especially if you're continuously recording, temperature throughout the day, it's important to kind of know, well, are we going to take the maximum temperature for that day, or are we going to take the lowest or the value overnight? And some people might think, well, I'm sleeping, why does it matter what the temperature is overnight? Well, one, if energy companies might care about that, because if there's really warm temperatures, people might be using their ACs more. And also the science has shown that temperatures have been increasing overnight. So it's an important factor to look at to some extent. Or do you take into account both? You take the average temperature, which is basically max and min divided by 2. And there's other ones as well. I'm only talking about these 3. So that's something to take into account. And then I'll briefly just talk about the number of days. Again, it depends on who you talk to. I've had people say that 3 days is important, 1 day is important, 5 days is important. So, it really depends on how you define your project and what you want to get after. The rest of my talk really talks a lot about the threshold, about, determining heat severity. Are you above a absolute threshold, or are you above a 90-degree Fahrenheit value, or something more relative, statistically relative, where, a statistical percentile comes into play. So a lot of my talk, the rest of my talk will kind of go into this piece a little bit more. So, going back to, just heat severity, so there's if you're talking about something absolute versus something relative. So, in this case, this is a graphic that NOAA NCEI produces every month. They just released the report for August of 2021, like literally 2 hours ago. So they produce a lot of graphics like this. And what this is basically, it's an anomaly above some sort of fixed threshold. And I'll talk about that in a second. But you can also kind of contextualize it differently and say, hey, how many days are above the 98th percentile, and they're somewhat similar, but they're somewhat different. But as a data scientist, it's also important to know, you're saying above a threshold or you're above some sort of period, but what's the period? And if you look very closely, your periods can be defined differently. So on the left, they're actually using the 20th century average as their average period, or climatology, as we would call it. So they're using 100 years of data as sort of a baseline, whereas the graphic on the right is only using a 30-year baseline. So you may have heard, actually, I think there was a presentation last month or a few weeks ago from GHCRN talking about climate normals and how they just released a new set of 30-year normals for 1991 to 2020. So obviously this graphic's already outdated because they're using older normals. But it's really important to understand, what is your baseline here? Because on the left, your baseline is 100 years of data, and on the right, it's only 30 years of data. So going back to what I was working on, we had to figure out, we wanted to create some sort of climatology, but I had mentioned that our data only goes back to 2009 because that's when not all humidity sensors weren't installed until that year. So we needed to figure out, well, how do we create this baseline? Well, thankfully, we had literature to kind of back us up on this. And there was a group here about 10 years ago made what they called hourly normals. But they only used a period of about 10 years, which according to the WMO is not necessarily the right thing to do because they say use at least a 30-year base period. But we really wanted to bring in a lot of weather stations and airports that we call ASOS stations, but they weren't really installed until the mid-90s. So we didn't have a full 30-year period yet. And in some cases, we only had like 9 or 10. So they kind of came up with a aggregation piece or a way to kind of create a window, plus sort of a 15-day window where they would gather all the temperatures within that, within that specific hour and within that 15-day window. And they showed that you basically had enough data to create a big enough distribution to create essentially a 10-year normal. So we did that. And we did the same methodology. So we basically, not only do we have hourly and 5-minute data going back to 2009, we also have this sort of climatology. So we can now say, hey, this particular day at this CRN site was, warmer than normal, or, higher than a certain percentile metric. And I'm going to quickly go over a couple of case studies here using these methodologies. So first, in the southeastern US, in about October 2019, we had a really, really warm day. Usually by October, things start cooling down here. We don't get as much flow from the Gulf of Mexico, so we don't get a lot of humidity. It usually things kind of settle down in October, but not on this particular day. In fact, the Raleigh Weather Service had posted that their ASOS station at the airport actually reached 100 degrees. And I think it was the first time it hit 100 there that season. And it was definitely one of the first times it hit it in October. So it was a really warm day. Well, thankfully we had a CRN site within, I think, about like 5 or 6 miles of the airport. And so I was able to kind of plot the data. And what you're seeing here is it's in the town of Durham, and there's a lot on here, so I do apologize, but what you see on the top is what just the regular temperature would be, and on the bottom would be what heat index is. And sort of these dashed lines are it's the hourly data and the hourly climatology that we had developed using this sort of this 15-day window. And just if you just look at the dashed lines, you can clearly see that it's much warmer than normal. In fact, I think this was I think it was two standardized anomalies higher than normal for a day in October of 2019. And then when you sort of look at the 5-minute data, there's 5-minute data here, and then there's smooth data as well. You start to see these really interesting features where it actually really warms up earlier in the day, and then it, obviously, and then it cools off later in the day. But heat index, it's kind of hard to see, but heat index, it kind of flattens out throughout the day, and it's kind of more, you're consistently at 95 degrees for a lot longer than you may have been for just looking at just temperature. So in this case, it really is not necessarily just the heat, it's the humidity as well. The next slide shows it's still dry bulb temperature on the top, but it's wet bulb globe temperature on the bottom. So kind of focus on and it's the same y-axis for all the graphs. But if you kind of compare heat index on the bottom here to wet bulb globe temperature, it's definitely, it appears to be cooler, because again, it's the way the numbers kind of work out, in that it's perceived lower, but it's just as severe. And actually, you almost have, with heat index, it kind of flattens out at 95 from about, let's say 11 a.m. local time till about 6 p.m. local time. But wet bulb globe temperature, you're actually at a really bad threshold of 85 for a lot longer. You're pretty much hovering at the 85 degree mark for most of the day. This is you have this big jump when the sun comes out, because solar radiation is a factor. And then as the sun slowly sets, it kind of tapers off. So you kind of start seeing these nuances depending on which metric you use. If you use wet bulb globe temperature, you might be at a more severe rate throughout the day, but people might go, wet bulb globe temperature of 85, that's not that bad. When in fact, according to that chart I showed earlier, 85 means you can be outside, if you're out practicing or doing yard work, can't be out for too long. You need to take as many breaks as you possibly can. The other example I want to show is out in the Southwest. Now, I haven't mentioned this yet, but a lot of the offices out there don't really use heat index, because the way the equation is set up, it has a tough time handling really dry data. And out in the West, we don't really, it's usually drier out there. In the southeastern US, we have this flow from this southerly type flow that brings in all this moisture from the Gulf of Mexico. Well, that doesn't always happen out west. Especially when you're not in monsoon season, excuse me. So this case study is going to look at the USCRN station that's not too far from the infamous Death Valley site that recorded a temperature of 130 degrees. And I don't think it's been verified just yet, but if it does get verified, it will be the hottest temperature officially in July, it's the hottest official temperature since the July of 1913. I think that was 134 degrees Fahrenheit. So we have a CRN site about 15 miles away from the station. And so so you have dry bulb temperature on the top again, and heat index on the bottom. And so the first thing is that out west, as I had mentioned, heat index has a hard time with really dry conditions. And as a result, it actually almost incorrectly lowers the temperature. So, the high temperature at this particular station was 125, I think, but the heat index was only 112. So this is why out west, they don't really use heat index. So again, it kind of goes back to what what metric you want to use, because it can vary. And again, this kind of goes as to why we don't necessarily have one metric to rule them all. And then again, with wet bulb globe temperature, we have the same problem, in this case, it does account for humidity a little bit better than heat index, but you still have this weird communication issue. If you tell people, hey, it's going to be 92 degrees at Death Valley, they're going to go, oh, that's fine. That's almost like a fall like day for us to hear. So, you know, it can be a communication challenge. And then the other thing about wet bulb globe temperature that you can definitely see here, and I'm not sure if you were able to see on the other slide, but it's a lot more, especially the sub-hourly data, the data we have at 5 and 15 minutes, it's a little bit more jagged. And because it's very dependent on it's very dependent on the sunlight and the wind. So if you have a really calm wind value, or if the sun or if a cumulus cloud goes over for a little while, that can really affect your wet bulb globe temperature. So it's definitely high. It's definitely more sensitive to those things. Okay, so we're still kind of, I may have been jumping around a little bit on these slides, so I apologize, but I want to kind of come back to this threshold mechanism for a second. So, you know, you can either have a fixed threshold of 90 degrees Fahrenheit or something relative, where, you know, if you have a distribution of temperatures, you're kind of picking off, like, let's say, you know, an extreme 98th percentile. So you're looking sort of at the tail of that distribution to see, you know, where, you know, the highest temperatures are. And it may not necessarily correspond to a fixed threshold, because again, a 90-degree day in Boston is different than a 90-degree day in Miami. So what you're seeing here is some graphics from the literature. On the left, you're seeing, and I believe this is outdated, but this is what the National Weather Service used at one point to develop warning criteria. You know, so how they determine heat severity for when they issue, you know, an excessive heat outlook or a heat warning. And then on the right is I think this is so it's the 90th percentile summertime temperatures that you could use for, this was specifically for helping out MAP, like outdoor athletic associations, and they use wet bulb globe temperature in this case. And in both cases, you have, you know, spatially different values. You know, you're going to have higher thresholds in the Southeast US just because it's generally warmer there, and you can certainly see that with the relative thresholds as well. So this is kind of where, if you follow me on social media, you know, this is something that I like to call the research hill I've decided to die on. And it's basically, I'm going to make a case for relative thresholds versus absolute thresholds. And the reason why I'm decided to take this hill is while I was working on this paper, I was trying to figure out heat severity of my own, how to define it. And I was just curious because I live in North Carolina, and I was like, okay, well, let's see how many excessive heat warnings we've had in North Carolina. And and I live in the mountains of North Carolina, so I would imagine that I would have less than, you know, some other areas of the state like Raleigh or Charlotte, or even in other major metropolitan cities like Atlanta or Greenville, Spartanburg. So I went to generate the graph, and I was surprised by this graphic. What you're seeing is the number of heat advisories that was issued in the state of North Carolina since about 1986. And I had kind of expected we'd have lower values than, you know, the rest of the state, but none. We had zero heat warnings, or excuse me, zero heat advisories issued. This is where I live. I live in Asheville, North Carolina. This is Buncombe County. This is the county where Asheville's in. I was really shocked because, you know, I have people, you know, I'm from New England. So I moved down here and I was like, oh, you know, the heat's terrible down here in Asheville. And everyone's like, nah, you don't live in Charlotte. You don't live in Atlanta. It's not as bad. But are you seriously telling me we've had no heat advisories? That was kind of surprising for me. And I did a little digging. And the reason is, in the state of North Carolina, regardless of where you are, you have to have a heat index of, it's either 105 or 110. I can't remember, but you need to have something really high in order to trigger a heat advisory. Well, that's never happened here. I think the highest we've ever hit here in Asheville was like 100 or 101 heat index. But just because we don't get to 105, that doesn't mean we don't have heat related illnesses or any issues with heat. So, and that's basically the hill I've decided to die on. And, you can kind of see that in this graphic. This is some preliminary health data we were able to get, and it shows the number of people that were hospitalized for heat related illnesses over a few years. And we had done a hinge fit analysis. And what this is basically telling us is this is so like, for example, in July, you need it. If Asheville has a temperature higher than 90.1, then that's when you start to see an uptick in hospitalizations for heat related illnesses. And that's nowhere near the 105 mark that the Weather Service uses. And even in Durham, it can be, it's a little bit higher, 91.6. And even if you don't have health data to consider, and you just looked at these relative thresholds, so this is the 90th percentile, the 95th percentile, and the 98th percentile. Let's look at the 98th percentile. That's the extreme of the extreme. Those are the tails of the distribution. Asheville is not even 91. Again, not even close to the 105 threshold. And 90.8 somewhat syncs up with 90.1 when you see an uptick. And, in Durham, okay, you're at 101 in Durham. Okay, that's close. That's close to the 105 threshold. So you can, in theory, get your heat advisories issued for the county that Durham's in. But Asheville, it just seems bonkers that you have to stick to an absolute threshold of 105. What if we use these relative thresholds? Yeah, maybe a little harder to convey to the public, but you don't necessarily have to use numbers. So this is the Asheville station. And, simply by just changing to relative thresholds. So on the top are using fixed thresholds, and on the bottom are using absolute or relative thresholds. And what you're seeing is basically you're seeing more hours above thresholds using the relative metric, and this can also, in some cases, solve your communication issue with wet bulb globe temperature. Because again, wet bulb globe temperature, a severe WBGT is 90, but you don't necessarily have to tell the people that. If you say, if you use these relative thresholds, you don't necessarily have to tell them what the number is, but you can definitely get a number of hours above that threshold. So, you can, and I know some Weather Service offices are using this, especially out west, where they're not necessarily telling them, hey, it has to be 95 degrees Fahrenheit. They'll just say, hey, we think it's going to be an elevated risk or a high risk or something like that. So it's just something to necessarily think about. And, I've been picking on Asheville a little bit. Again, we're in the mountains of Western North Carolina, but I mean, this is everywhere. It's not just here. So these are all the USCRN sites at the CONUS level. And this is a particular year. This is 2012. It was one of the warmest years on record for the lower 48. And if you just do a fixed threshold of 105, and I know that's not fair because it's spatially, it can be spatially different, but you don't really get a number of hours if you're above an absolute threshold. But by changing it to some statistical percentile, again, this goes back to what happens in Boston is different than what happens in Miami, which is different from what happens in Denver, which is different from what happens in Austin, Texas. So, by doing a more percentile based approach, you might have, more hours under an area, which would then help the Weather Service. Now, you may all think that I'm knocking the Weather Service. I'm not. I mean, I partner with them on some projects, and I go to them for forecasts. So I think they do a wonderful job. But this might be something to consider if you want to help continue to warn the public about heat. And I had mentioned this. I don't think I have a graphic in this talk, but in the western part of the US, the western region of the Weather Service, they have a product called Heat Risk, which inherently does a lot of this already. So they are using a lot of these types of statistical methods. And then, yeah, this is sort of my second to last slide. So just future work. I work for the USCRN team, so it's 139 stations in the US and Alaska, mind you, and Hawaii. But we want to apply this to other stations. The next logical step is ASOS, which again are airport weather stations. And they have a lot of that information. And then, for those that are data savvy, if we don't have a variable, we can always pull it from a reanalysis data set like the 20th century reanalysis or ERA5 from the Copernicus folks. And then, we're really good at talking about climatic exposure, but we can also map this to, vulnerability. We can kind of match up this data to people that are, to socioeconomic data, to census data, to health data, agriculture data, to see, who's actually more vulnerable to these types of events. And then, I had mentioned, we did a little analysis with health data, but we want to do more. But if there's one thing I've learned is that getting health data can be very tricky. We're very, as a sort of weather and climate enthusiast, I have become very appreciative at how much our data is easily accessible to some extent, because it's a lot harder for health data and lots of other data sets. All right, so these are my key takeaways. I'll just leave it at that. Thank you all for listening. My email is below. Feel free to, if you want to chat more about it. I didn't put it on here, but I'm also on Twitter, JJ Rennie on Twitter. I go there and post cool stuff and talk about a lot of heat stuff. So yeah, that's it. Thank you all for listening for the past half hour. And I think I saw a couple questions come through, and somebody may have raised their hand, but I am happy to help answer any questions you may have.
Great. Thank you so much, Jared. That was fascinating. We did have a question actually about that last point that you were kind of talking about, the availability of data. And someone was asking how you got the hospitalization data.
Yeah, so that specific data, and I shall caution that is preliminary, not finalized stuff, but it was, we partnered with some folks in North Carolina. Our organization is part of the NC State system, and we made some connections with the health department to get that data. But just to reiterate, getting health data is hard. Getting weather and climate data. I mean, you can go to multiple places. You can go to NCEI, you can go to the cloud, you can go, and there's different formats and such, different models, GFS, NAM, HRRR, different nuances about the data, but you can get that data. It's mostly, I mean, most data is easily accessible. So that's not the case for health because, well, one, because it is, personal identifiable information. So, they have to basically aggregate that data and do some quality control on it before they even allow it to be released. And we have to sign contracts and such. So it's, yeah, so I was really surprised to find how difficult it is to get it, but I get why.
Yeah, no, that's one of the amazing things about the weather and water climate communities, how much data is available out there. And there was a lot about kind of the localized impacts of heat and the kind of local recipes for heat warnings that you were talking about. And so there's another question related to that. If we could get your thoughts on warning and mitigation strategies for marginalized, vulnerable inner city populations that are disproportionately impacted by heat.
Yeah, and that is something, I know local weather service offices will do that to some extent, and emergency manager offices will do that to some extent. Yeah, because that is I think that at least me personally, like that's sort of the next step is, you can say, let's just take a county or take a city, right? And let's just say it's going to be 100 degrees in that city. everywhere. There's for sake of easiness, it's just going to be 100 degrees everywhere in that city. But certain areas are more vulnerable, right? You have different types of housing. Some people have air conditioning, some people don't. Some people have green roofs, some people don't. Some people may have a car so they can go drive somewhere if they need to. Some people don't. Some people rely on public transportation. If a cooling center shows up, if you're within, let's say 100 feet of a cooling center, you can walk to it. But if you're not, you may have to walk, it could be a couple miles away. And then if you don't have transportation or can't get access to it. So this whole vulnerability aspect of it, like as to who's really affected by it, that's a fascinating piece of research, at least for me, because I'm a climate scientist. So we would need to partner with the emergency managers, with the city, with weather service offices. You basically need to have a really good team to kind of figure that out. And then I will also kind of side mention that there's this, some of you may have heard that there's this big campaign going on to mapping out this urban heat island stuff. I think this year, like 4 or 5 cities started doing this campaign where they would go out with thermometers and kind of do like a mapping of like what areas have higher heat, based on asphalt or concrete. So I may not have an exact answer for you, but I know that that's sort of, at least from a climate scientist perspective, that's the next step.
Along those lines, there's been a lot of community and citizen science projects that have to do with heat monitoring and data collection there. Do you see more opportunities for those sorts of projects? And is that data kind of useful? Do you think there are pipelines that could be created?
Yeah, I think so. I'll reference again this project that's done by the Climate Program Office. Is that I think they're in their 4th year of doing it. I think, I don't remember all the cities, but I think like Charleston, South Carolina, Atlanta, Georgia, Raleigh, Durham, North Carolina, they will go out and, collect some of this data. Somebody, don't quote me on this, but I feel like that data is publicly available for people to analyze and integrate into their work. And then there's other citizen science projects as well. Like I know there's one for that one specifically for rainfall. It's called CocoRAS, but I have to believe there's something else out there that does, temperature measurements. I just don't know off the top of my head.
And there's also a question about getting back to that miscommunication or communication piece. Why not just add 10 or 15 or 20 degrees to all of the globe temperatures, I guess, to create better communication around that?
Yeah, I thought about that a little bit because I think someone had suggested that to me at one point. It's hard because the way the equations, like all 3 of the variables, wet bulb globe temperature, apparent temperature, and heat index, all essentially are on the Fahrenheit scale. So I mean, yeah, you can in theory add 10 degrees, but it doesn't necessarily make sense to do it that way. Now, if a social scientist comes and says like that's exactly what you should do, to make it perceptible to like 100-degree heat index is comparable to a 90, then maybe that's a route. But I think what we're doing instead is, and I didn't exactly mention this, but for those of you that may have heard of the drought monitor, the drought monitor, it's done by drought.gov and NITIS and a few other folks, is that every week they'll produce a map of where they think drought is occurring. And they have I think it's 5, maybe 5 or 6 categories, but it goes from like D1 or D0 through D4. And they never actually tell you what the value is. They don't tell you like, oh, well, this drought value is, 3.7 versus this drought value, which is 4.2. They just give you a categorical system. So they just say D0, which is abnormally dry, to D4, which is like a severe drought. And that may be, or at least I would hypothesize that may be the route to go, where you don't necessarily give people a temperature. nor do you have to say like, oh, well, take this value and add 10 or subtract 5. You can just say like, hey, this category is an 8, like I'm just hypothesizing, we're theorizing, where you can say, this is H0, not that bad, go outside, versus an H4, okay, don't go outside. If you have to be outside, take breaks, check on the elderly, check on kids, make sure kids aren't in cars, things like that. And maybe that's the better route. But maybe some people are screaming at me, like, people want the number, right? So maybe people want to know that 120 is high. So, it's almost kind of like the weather scale to some extent, where, and now I'm just rambling and talking out loud. I will talk about this forever. So if somebody wants to stop me, feel free to stop me. But if you look at a lot of the stuff with hurricanes and tropical cyclones, you have the Saffir-Simpson scale, which is based on a wind value, and if you have a wind value of 154 miles per hour versus a wind value of 155 miles per hour, that's a 1 mile per hour difference, but that's the difference between, let's say, a category 4 and a category 5 storm. So, you have some people say like, well, don't focus on the number, focus on the impacts. But then some people, they may or may not take action unless there's a category 3 or higher. So it becomes, and this is where, as a climate scientist, as a weather enthusiast, this may not be my realm. This may not be something that I can be the expert on. This is where we have to have, like I said, that team. This is where we need to have a social scientist that says, the public focuses more on this. And then you need to have the emergency managers that say, hey, let's focus on these vulnerable populations. And then you've got the weather service people who know how to disseminate the warnings and add the text and such. So essentially, it just kind of comes back to building a really, really good team on top of this research.
Yeah, that team is fascinating. I'd love to get your list of who should be on that team. But we did have another question about the wet bulb globe temperatures. Do you think it'd be useful to include them in everyday weather forecasts so that the general public would begin to understand them?
I think that's a start. And I know the Weather Service is already doing that. Some offices are. The ones I know off the top of my head is, the Raleigh office, Tulsa, Oklahoma. I want to say Minneapolis, Caribou, Maine, I think. They're starting to do it. And what are the results? I'm actually not sure. I'd have to go talk to them a little bit more. I know Raleigh is super interested in it. And then, like I said, the at least for the weather nerds that look at the weather models, the NDFD has it. It's in there as a, it's experimental right now, but they incorporate it. And then they actually have different categories of like low, medium, high. So, which one's better? You can make arguments for both. But yeah, I think it would, again, it'd still be a communication challenge because people are going to be like, I can't, I joke to people, wet bulb globe temperature, say that 5 times fast. So it's like, it's another thing. Do people want to do it? Should it just be heat index, And then, we haven't really talked about the private sector, like AccuWeather has the real feel, which may take into account some of these things. So it like I said, it's a huge communication issue. And my mind is just like melting from just like thinking about all that.
Well, thank you for sharing your thoughts on it. It's really fascinating to hear the perspective and another reason to get to know your local forecasting office. And then also that's a really good point about the private sector. I think this next question gets to some of your relative versus fixed thresholds, but do you take into account that some populations are used to higher temperatures?
Yeah, and that's my case for the relative thresholds. That's the research hill I want to die on, because even in North Carolina, again, I'm absolutely not knocking anybody here, but like in North Carolina, when you have, anywhere in the state has to be 105 degrees. It never hits 105 degrees here in the mountains just because we're at a higher elevation. But if that was lowered to, let's say, 95 here, then, you're going to start seeing different numbers. And then yeah, cities like Charlotte and Durham, the lower elevations, Wilmington, they do experience higher temperatures, so the relative threshold in my mind really makes more sense. It really does. And again, I'm just talking about North Carolina, like even in Florida could be, a 95-degree day in Florida can be nice depending on who you talk to. So yeah, so that's, and like I said, this National Weather Service heat risk, that's what it's called. If you have a little time, go ahead and Google and take a look at it, because it's the Western Region headquarters. They've really developed this really nifty tool that it uses that, where they don't exactly give you a category, they don't exactly give you a number, but they give you a category, and those are based off of percentiles, where they say like, hey, this part of like Death Valley, Death Valley is also one of the lowest places on Earth. That's why it's so warm, because generally as you go down a valley, generally speaking, it's you get warmer. So, even Death Valley is going to be way different than San Francisco. So, and I think they've done a really good job at taking that into account.
Fantastic. Well, thank you so much. I think that covers all the questions that we had come in. So again, thank you for walking us through all of this amazing information. And thank you for doing it in a mask and persevering through that. We really appreciate you being here.
Thank you so much. And it's a nice day out here. It's actually not bad outside, so I might actually go for a walk now. But yeah, thank you.
All right, well, enjoy whatever temperature it is there. And thank you all for spending some of your time this afternoon with us, and have a great and wonderful rest of your day.